Sarkar. Just wanted to share a video with you for the next 20 to 30 minutes. Overall intent of this video is to share an end-to-end machine learning project, and also the intent was to show you an innovative way by which you can actually find quality data sets. I see a trend going on where we highly rely on the data sets, what we are seeing in Kaggle, but there are other ways by which you can actually find quality data sets and work on them. So the overall process would help you to search, quality data sets for sure, and to formulate your own use cases on top of that. So we would be also looking into the thought process which I followed. Maybe it could be something different which you can follow as well. I mean, it's open to everyone. So pretty much the machine learning process is quite flexible. In this life cycle, I would be taking you to the every step, like how I'm getting my data, how I'm preparing my data, how I am doing the feature engineering, the feature selection, and the model building part as well. Even the hyperparameter tuning is also covered, and how we can deploy this as an application. And so it's an end-to-end process. And you would be also seeing how you can utilize this to, add kind of a machine learning portfolio to your resume, or any projects you want to do, offline apart from your usual work. So I'm looking forward for feedback, some ideas as well, where I can implement this to generate some new content as well. So looking forward from learning from from each one of your feedback, and any questions or any ideas is always welcome. So let's go ahead. I'm going to share my screen, and we would be jumping into some, how we are extracting our data. So just give me 1 minute. I'm going to share my screen. Okay. So this is a website I was actually referring. If you see, this is data.gov. This actually has some really good quality data sets. For example, I did a search of diabetes data sets, and I could actually see 79 data sets just on diabetes. You can go ahead and extend your search to any particular thing. For example, I want to do cardiology, for example. You can get cardiology specific data sets as well. And if I want to do COVID-19, okay, 749 data sets on COVID-19. So these are all, maybe surveillance data, or, kind of symptoms as well. So all those data are pretty much down. You can download those data in CSV, JSON, or XML as well. So that flexibility is obviously there. So one of the data sets which actually grabbed a bit of attention of mine was this particular data set. It's kind of a photochemical smog and vitamin D deficiency. So this is kind of an experiment which was performed on mice. It was kind of a clinical trial done, and this is kind of a study for examining the impact of the vitamin D deficiency on the cardiopulmonary response of mice to photochemical smog. So this was the experiment which was conducted, and it gives you a pretty good description about what the data set is all about. So it's showing you on the adult mice and where it was conducted. You can actually download this with this option here to download. You can even open it with different formats, and there's a reference given to this particular data set. It has also the the owner who actually owns the data set, and kind of a publisher. So if we just deep dive to look into what this data set actually pertains to, you can see there's an abstract. You can download this as a PDF as well. So the overall intent of this experiment is to see what are the nutritional deficiency that has lead to cardiovascular susceptibility to an to an environmental exposure. So what is happening in this, the mice are fed with a vitamin D deficiency diet, and they basically track all the medical parameters like your heart rate, your heart rate variability, your, the VDD is nothing but your vitamin D deficiency diet. So they are basically seeing how a normal diet and a vitamin D deficiency diet actually, how, what is the response among mice in the population of mice. Now that's pretty much the data. If you look into, if you download this particular data, you can see there would be a lot of data. It's kind of a series of data sets. I'm using this particular data set here, and it's quite a huge data set. And you could see features like, the diet, the exposure, the log time, the breeding frequency, the tidal wave, sorry, the tidal volume, the inspiratory time, the expiratory time, the pen H, the age, and the time of the experiment. So these are the features. When I'm quickly the if I do a very quick glance, it's difficult to understand that what kind of problem it is, what kind of problems we are trying to solve through machine learning. So is it a regression based problem or a classification based problem? So let's deep dive. Let's first get this data to our IDE and see, explore this, how we can formulate the use case, and how we can take it ahead from there. So let's just deep dive. I'm gonna use the Google Colab IDE here. Here is where I have uploaded the data set here, and I'm going to start writing the code from here. This particular first code is to import all the necessary libraries which we generally use for machine learning. I'm assuming this libraries are frequently used by any data scientist doing basic transformations, and doing the exploratory data analysis or kind of feature engineering. So the overall intent was to get the standard libraries in place. Now, once I start reading the library, sorry, reading the data from here, I can actually see, I have see my data. It's the same data which I had showing you. This is kind of, I'm seeing the head of this data, the first 5 rows of this particular data. I'm going to do a quick, okay. So once I'm looking into this, I can see the log time and ID. Looking, my initial look and feel tells me that this particular features would not be that obviously ID would not matter much, and even the log time, like when you are actually conducting that experiment. So my initial feel says that this particular two columns would not be very much relevant for my model. So that's the reason I'm trying to drop this. But you can always try using the log time, maybe if you feel it's relevant. So you can always go ahead and you can always use that particular feature called log time as well. The ID, I don't think it's much relevant. That's why I dropped that particular column. Now, if I do a quick df.shape, it's quite a big data set. It has 6,46,759 rows, and there are 9 columns right now. If I do a quick df.info, it's showing me it's a mix of object, float, and float 64 and object data types in this. If I do a quick describe here, it is showing me the float variables, which has the summary statistics of that. I'm going to do a quick check of any missing values. So I would use the isNull dot sum function and see what are my missing values. I could see in the exposure column, there are quite a few missing values. Probably it's 20,918 missing values. So let's just first handle this. I would be using the replacing it by the mode function, the most frequently occurring value in exposure, and I'll do a in place true. You can use other methods. I mean, there are good number of ways to handle missing data. It could be, mean median mode, or you want to replace it with something else. But this is what I had actually, used for my transformation. So if once we are doing this, the missing values are automatically handled. And the next step, what we would be doing is to, use the label encoder to convert the standard the objects to a categorical sorry, the categorical variable to numerical variable. So you're using a label encoder, and once you're seeing now the most of the object columns have been converted to int. So it's a good mix of int and float right now. So all the categorical variables have been used. You could use one hot encoding, or you could use other ways for to convert your categorical variables to any specific category you want. There are different methods. I just use the label encoder for this. Now, if we go ahead, now I'm doing a is null sum right now. I can see all the missing values have been taken care of. There are no missing values in my data right now. And let's just do a quick, univariant analysis just to see um, how my actually my columns are actually, how my features are. So I'll be using the KDE plot. It's the kernel estimation plot, which basically depicts the probability density function of the continuous and the non-parametric values of my variable. So if you see, this is the code I've written to just do a quick, univariant analysis. I would say it looks into each of the variables, like the features like diet, exposure. It's seeing the reading frequency, the tidal volumes. It's actually showing me a good spread, like what are the value, how are the values spread among this particular features. So good amount of insights I can get. I can see my time of experiment as well, how it's distributed. Another kind of analysis I would like to see is, how my features are, I want to explore their linear correlationship between my, features. So I would be using the heat map, the correlation matrix, just to see how are the features related. I can see some of the features are, negatively correlated as well, and some are highly correlated as well. It gives me a pretty good understanding about the linear relationships of my features. Now, as a standard part, I would be doing some feature scaling, where I am doing a quick scalar dot fit. It's a standard procedure for any features, like just to standardize them. If you want to standardize the values, you use a scalar dot fit fit underscore transform for your data frame. I'm just doing the same for scaling the data set, just to normalize all values. Now, once I'm done with that, I really want to visualize my data now. Like, I'm still not able to understand whether this is a regression or a classification problem. So my standard approach was to get into a PCA to divide this data into two components using a PCA. So I'm calling this as PCA1 and PCA2, and you can see it has actually divided my data into PCA1 and PCA2. Those of you who don't know PCA, I would be uploading some of the contents about what is principal component analysis and why is it actually done. But overall, this is where I am, trying to visualize my data by reducing the dimension. So it's kind of a dimension reducing technique. You could apply LD as well. You could do a TSNE, but I had performed all this, but the PCA was working best in this particular model. So you can go ahead and try LDA or TSNE as well. Now, once done, what I'm trying to do is to um, classify this data. Overall intent, I could understand that, I can classify this data into particular clusters. And why am I doing that? Because I know I want to see a trend, like among the mice population, like what are the similar kind of mice? How can I put them into clusters? And that is the reason I'm using the k-means, just to see how we can, it's kind of a, I would say, I'm doing a hyperparameter tuning just to understand how many clusters I can actually use to divide this mice population. So I'm using the k-means algorithm, and it uses the WCSS technique to see what should be my appropriate number of clusters. So if I see the elbow method here, it shows me a distribution, and I could see elbow which is getting formed somewhere around 3. Here quickly in this diagram, that this shows me the number of clusters should be somewhere around 3. So I'm sure who has used the k-means algorithm, they could understand and quickly relate why am I doing this, and what should be the appropriate value of clusters. So you can even try with k is equal to 2, or you can use k is equal to 4. The k is equal to 3 was giving me kind of a good result. So you can always go ahead and use k is equal to 2 and even 4, even 5 as well. The hit and trial should be always used as a best practices among, when you're building your model. So that's one way into looking into it. So I would be using the three components, like the clustering into three clusters right now, and I will concatenate this PC underscore df with my original data frame and add a cluster here. So basically, I'm adding this cluster to this particular by concatenating it by my pca.df, which we have divided into PCA1 and PCA2, and we would be visualizing this into clusters. Now, if I just do a scatter plot and to visualize my data of which was there in PCA1 and PCA2 in clusters, here is what I can actually visualize my data. So what does this actually show? This is actually showing me that the entire mice population has been divided into three clusters. That's 0, 1, and 2. And here you could see the spread of data. The blue ones are showing the mice which are of that particular cluster. That's cluster number 2. The green ones are the mice population, which has shown the similar kind of trend. They are into the green ones are into cluster number 1, and the amber ones which are into cluster 0. So this is you can easily visualize your data, like how your population or your data has been divided into three clusters. You can obviously, as I said, you can divide it into 4 clusters as well, and you can do those hit and trials just to make your model much more robust. Now, once we have you know we have visualized this data into three clusters. Now, what I would do right now is to quickly go ahead and find my cluster centers. So I'm basically trying to see what are my cluster centers. Once we get the cluster centers, we would be using we would basically inverse the data and transform the data so that we get out we basically get the original data back out. So there are two steps here. One is obviously getting the cluster centers, and then you basically try to inverse your data to get back your original data. So this is where I'm getting back my original data which was there. So once we inverse this particular data, what I'm going to do next after this, and I'm going to add a cluster to this, like what you said, after the time of experiment, I'm going to add a cluster to each one of them. So this is what I have done the concatenate, that we have added the cluster column here. So this clearly shows me where my data, like for example, if the diet is 0, the exposure is 2, or the breeding frequency is this particular entitled volume, this falls in cluster number 1. And if I go ahead, if I see this particular, if the diet is this particular spec, and if the breeding frequency is this would be my cluster number 2. So I've basically, converted this data to a classification problem right now. So I've used the k-means clustering to cluster my data, and this is where my data has been divided into clusters. Now, going ahead, what I'm trying to do is I have concatenate this again with my original data frame, that's TF, and this is where my the original data looks like. It has all the columns, but the only addition I'm seeing the cluster column here. Now, I'm basically trying to see how my clusters actually look like. I can see the count of the mice population here. This is cluster number 0, this is cluster number 1, and this is cluster number 2. So that's how the data has been divided into three clusters. Now, taking ahead, if I really want to visualize this much more intuitively, I would be using a Seaborn facet grid option, where you can actually see how your clusters actually look like when you compare it with each of the features. Now, if my diet, if I see my diet feature, this is how the cluster 0 looks like. If those values of diet are following in this particular range, it will be a part of cluster number 1. If the diet range is falling in this particular range, this would be my cluster number 2. So I'm basically trying to visualize my data in each of the features I'm trying to visualize this in cluster 0, 1, and 2. So I can do it. It's doing with all the features I had here, with the expiry time, the pen age, even the age, and the time of expiry. Once done, you know, I will convert this into an CSV file, and I could actually split this, because what I have done right now, I have converted this use case to a classification problem. If you see, if you go ahead and see the data set right now, so these are all my these are all my you know independent features, and this is my dependent features. This is the cluster. This would be my y and x. I'm basically dividing it into x and y right now, because I'm using the test and split right now to visualize my data. So this is my explain. You can even visualize your x test as well. Now I can quickly use any of the classification techniques. I'm using a decision tree classifier, and I'm giving a criteria of entropy, just and doing a quick model.fit. I'm doing my prediction, like if I look into my data, how it actually, look, which would actually get into a cluster number 1. So if you can see this use case, like if I pass parameters, the given parameters of, the diet, exposure, tidal volume, the inspired rate time, or the expired rate time, and panache. If I pass those features, it would actually tell me that this particular feature or this particular mice falls in this particular cluster, like cluster number 0, cluster number 1, or cluster number 2. Are you using a quick confusion matrix? You can see it's a 3.3 confusion matrix, because there are 3 clusters. If you want to do a cluster 4, it again becomes a 4 by 4 confusion matrix. Pretty good results I'm getting. The precision, the recall, the accuracy is close to 100%. It's 99%. So the model is doing a pretty good job to classify. First of all, the model has um, divided the data, or the mice population into 3 clusters, and then it's basically classifying it into those categories of cluster number 0, cluster number 1, and 2. And I can actually import this particular file into a pickle file. So overall, it's giving me a 98% accuracy. And we have seen how we have formulated an end-to-end use case looking into any data. So overall, intent was to give your thought process. You can obviously use your own approach. I basically use you use the unsupervised technique, learning technique, to use of clustering using PCA, and converting this to a classification problem. But let me know if you want to use some other approach. I would be sharing the code as well, so that you can quickly see what the overall thought process was. But looking forward for some ideas, or if I will share the data set as well, so that it would be intuitive for all of you to set up your own use cases, and the in your own thought process to for model building as well. So thank you so much. Really loved sharing this with you all, and looking forward for your feedback. Thank you so much.